In this video, we will cover Traceroute. Where ping tells you whether a destination is reachable, Traceroute tells you how traffic gets there. Every router hop along the path, the IP address of each hop, and the latency at each step. It's particularly useful for diagnosing routing problems, identifying unexpected devices in the path, and confirming that network changes had the intended effect. Traceroute works by exploiting a mechanism built into IP routing, the TTL, or time to live field in every IP packet. TTL is a counter that starts at a value set by the sender, typically 64 or 128, and it decrements by 1 at every router hop. When a router decrements the TTL to 0, it discards the packet and sends an ICMP time exceeded message back to the sender. That message contains the router's IP address. Traceroute uses this mechanism deliberately. It sends the first probe packet with a TTL of 1. The very first router in the path decrements TTL to 0 and sends back a time exceeded message, revealing that router's IP address and round trip time. Traceroute sends the next probe with a TTL of 2. The first router decrements to 1, passes it through. The second router decrements to 0 and sends back its time exceeded. This repeats, incrementing TTL by 1 each round until the probe reaches the destination and the destination sends back a final response. The result is a sequential list of every router the traffic passed through on its way to the destination, numbered in order, with round trip time measurements for each hop. The command is Traceroute on Windows and Traceroute on Linux and Mac OS, followed by the IP address or hostname. Each line of output shows one hop. The hop number, the round trip time, usually shown as 3 measurements from 3 probe packets, and the IP address or hostname of the router at that hop. Round trip time increases as hops are added. More routers in the path means a more processing and more distance the packets travel. A hop where latency suddenly jumps significantly suggests either a WAN link with a propagation delay at that point or a congested slow router. An asterisk where the IP address should be means that hop didn't respond to traceroute probes. This is common. Many routers are configured to not respond to traceroute probe packets because it exposes the network topology and can be misused. An asterisk doesn't necessarily mean the path is broken at that point. The hops beyond the asterisk often respond normally, and the destination is reachable despite the non-responsive hop in the middle. The last hop should be the destination IP you specified, confirming that the path completed successfully. In OT environments, Traceroute has specific security applications beyond general diagnostic use. Identifying unexpected devices in the network path, for example. 2 devices that should communicate directly through a switch with no routing in between should show 1 or 0 hops between them. If Traceroute shows a router between 2 devices that should be on the same VLAN, something is wrong. Either the VLAN configuration has changed, a device has been inserted in the path, or the network architecture isn't what the documentation says. You can also use Traceroute to confirm firewall placement. A traceroute from a device in the engineering VLAN to a device in the field control VLAN should pass through the firewall that's supposed to be between those zones. If the path doesn't include the firewall's IP address, traffic may be taking a route that bypasses the firewall entirely. You can also verify the effect of network changes. So after a routing change, VLAN reconfiguration or firewall update, Traceroute confirms that traffic is actually following the intended path. Documentation and intentions are one thing. Traceroute shows what is actually happening on your network. Diagnosing WAN path anomalies for remote SCADA sites can also be used when you're using Traceroute. If a remote RTU is experiencing high latency or intermittent communication loss, Traceroute from the central SCADA site toward the remote RTU reveals where in the WAN path the problem is located. A hop with consistently high latency or packet loss points to the specific link or a router that's causing the problem. Most OT devices, PLCs, RTUs, managed switches, will appear as expected hops in a traceroute path if they're routing between subnets. PLCs that sit on a single VLAN and don't participate in routing won't appear as intermediate hops. Some OT devices don't respond to ICMP at all. either because they're configured not to or because their firmware doesn't implement ICMP responses. In those cases, the device will appear as an asterisk in the traceroute output, even if it's online and processing control traffic normally. Understanding which devices in your environment respond to ICMP and which don't can help you interpret traceroute output correctly. As with ping, Traceroute sends a relatively small number of packets compared to a port scan, making it safer for use in OT environments. However, the same caution from an earlier video applies. In a production OT environment, know what you're testing and confirm it's appropriate before running any active tool. In the next video, we'll cover host discovery using router and switch CLI commands, which is another passive approach to finding what's on your network.